In this second session, the new networks of communication for digital transformation, the chair of this section, José van Ooteghem, from FTTx Belgium. Have the floor.
Okay, thank you very much, Miguel.
Una hora.
Yeah, okay. I'm also pleased to chair a session of this conference, session 2. I hope you're not yet hungry and you can stand another hour with us for a few interesting presentations. It will be about new networks of the communication for digital transformation. I don't think I have to explain what is a digital network. In the previous session, it was a little bit more difficult. Industry 4.0 needed some more explanation, but networks, that's every know what networks are. As we only have 1 hour for 4 presenters, I will give most of my introduction time to the presenters, so I'll keep it very short. In this session, like I said, we have 4 speakers coming from Spain, Greece, and Belgium, and they will tackle different technologies to transmit information through the networks. The first presentation will go about the major change in distributing and watching TV content. Then we go to the fixed network, about new GPON technologies that can be used in the fiber access network. Then we go to the mobile world with new technologies in the future 5G. And the last presentation we go back to the fixed network about optimized design of fiber to the X networks. I suggest that we keep the question and answers at the end, because there will be maybe some questions for different speakers. So it's 12 minutes for every speaker normally in that 1 hour. We go now to the first speaker. And the first speaker is Mr. Fernando Diego Hernandez Martinez. He is telecommunication engineer, a specialist in audiovisual systems and now studied at the University Carlos III in Madrid. And Fernando has a special interest in video infrastructure, audio applications, and television technologies in a global market. Now, in television, there are 3 main revolutions. There's a technical revolution, as you know, that in the past, not so long ago, there was analog TV coming from the air or coming via the cable television, but now we have all digital TV. Second thing is also about the content. Now, the classical TV stations are still there, but you have new content via internet, Netflix and other providers. So there is a variety of content now. And another thing is also the way we look television. In the past, it was direct looking to television stations. Today, most of the people are looking delayed. So there is a lot of revolution also in the television. Okay, I give the floor to Fernando first.
Thank you, José. Okay, presentation. Okay, good. All right, hello everybody. Thank you for coming. I'm really glad to be here, so I can be able to talk a little bit about the research we made in front of all of you experts and colleagues of the field. I speak on behalf of my research team, which is formed by Julio Navio-Marco, that you probably know, is here, and Raquel Pérez Leal, which is a research professor at University Carlos III of Madrid. Well, we did an analysis on the broadcast technologies enabling the, we did analysis on the technologies enabling the broadcast convergence. So I'm gonna talk a little bit about how is the sector nowadays, which was our main target, and we will end with the conclusions we found after we did the work. Let's start with a quick introduction here. Telecommunications, and especially the broadcast television industry, is continuously living on a reconfiguration and integration. Broadcasters must integrate new technologies into their services in order to keep the leads facing the emergence of new actors that never existed before in the market. New access technologies, platforms, and services have altered the economical balance of the industry. They have strongly impacted the 21st economy, the 21st century global economy, and the most important part, they have provoked a relevant societal transformation. There's an increasing interdependence between the companies involved in the entertainment sector and the firms related to the delivery and processing of information. Besides that, there is also a move that translates the added value of the communications from transport layer services to the application level. So the main goal of our project was to analyze the technological change and its impact on the broadcast sector, as I said, which is now in a critical moment of evolution. What is happening on the sector? Well, we have, of course, technological changes from traditional broadcasting to connected television, IPTV, or mobile technologies. We also have an integration and convergence of services among actors. Telco operators, media producers, and distributors of content, now they mix each other, and the borders between them are bluer than ever. We also have radical changes on the consumer behavior, and this is a key point, especially with a high increase of digital natives entering the market. And last but not least, we also have drastic changes in the regulatory framework, with especially the assignment of a critical resource, which is the radioelectric spectrum, limited and expensive. After research, we found a clear statement: keep up or be displaced. Keep updated, integrate new technologies, or you will be displaced. There is no room for settlement in the sector. If we talk about the main part of the project, which was the technology evolution towards the integration, this evolution has been the key in the transformation of the sector. Group number one of changes, we have new system and access technologies. As I mentioned before, for example, new broadcast systems through optical fiber or IP protocol-based solutions. We also have a big group of changes in new devices, smart TVs, cell phones, and tablets that open new possibilities like second screen or a social television, which has a completely different market from the traditional systems. Group number three of changes, we have a digitization of the communications with new platforms and services. The convergence of these three main areas of changes makes possible new ways of accessing media communications from multi-platform, from anywhere, at any time. However, we found that there has been an initial restlessness with respect to the future of the sector, and a certain resistance against the obvious changes, maybe caused by the fear or the uncertainty that traditional broadcasters have seen with the new actors coming into the broadcast sector. So no doubt this is a question about survival in the sector. If we talk a little bit about technologies, access technologies and services, we could say that nowadays there is a big coexistence of different access technologies. We have radio with digital terrestrial television or satellite TV. We have wired access technologies with cable TV or IP-based solutions. And lately, we have new generations of mobile broadband networks like 4G and the upcoming 5G that we've been talking about all morning. This coexistence, along with the restructuring of the spectrum and the possible convergence between mobile broadband networks and television broadcasting, evoked inevitable changes on the fixed television networks. Moreover, this multi-tech scenario has also changed the consumer and television consumption. While DTT and cable keep at the standard trend in the market, satellite and IP solutions are highly increasing their share of the market. So the competition for television now is among traditional broadcasters, new over-the-top platforms, and lately, new internet and tech giants like Apple, Google, or Facebook, who are moving onto the telecommunication and television services. We found really interesting how some of the traditional access technologies have evolved into the digital era. All of these, satellite, cable, digital terrestrial television, develop new versions of their standards in order to adapt to new high-quality content and the demands of the public. As I don't have much time, I won't go through all the details, but you can see the second versions of the standards allowing 4K transmission of video and more efficient use of the spectrum. I will just mention that the increase of bandwidth in the networks has paved the way to new television service providers, like IPTV or over-the-top platforms. Society is now currently on a period of hybrid consumption model that combines traditional broadcasting with the internet streaming. Technology keeps evolving, also in television, of course. We have 4K content, 8K. We have super ultra high definition, thanks to, for example, quantum dots. We also have high dynamic range for color and brightnesses. There is a growing demand for connectivity with better and higher speed broadband connections for this new technology. As it was mentioned before, it is necessary to keep working on new codecs and communication systems that reduce the latency to insignificant on the services, no matter what the platform is. It has to be transparent for the consumer where they watch TV. Doesn't matter tablet, doesn't matter cell phone, doesn't matter PC or smart TV. As an example here, we have Netflix that developed the new version of the most common codec, which is the H.264, the MPEG-4, and they're using it for their 4K transmitted video in their platform. We also have Google that they developed the VP9 codec for their 4K YouTube videos and their browser, Google Chrome. They have been able to reduce the bitrate for a full HD, 1080 progressive in YouTube, from 8.2 megabits per second down to 3. But they're trying to go further. With the VP10, they assure they will be able to reduce the bitrate down to 1.5 megabits per second, which is a really high step for efficiency and for new quality. Television broadcasting through the net, the upcoming 5G networks, the Internet of Things, machine-to-machine communications, a new whole level of connectivity has come. A complete convergence of the systems, which gives us, telecommunication companies, new horizons to fight for. Just a little bit about the emergence platforms. Television service forward now a mode of use in which the consumer wants and can practically choose and control what to see and when to do it. They have absolute control of a media center with the convergence of several television and communication technologies. With the digital market, the most disruptive platforms have been the over-the-top. But this has just not happened in the audiovisual, as you are aware. For example, we have Apple's FaceTime, Skype, WhatsApp. They offer telecommunication services. Well, we have Spotify, YouTube, or Netflix that broke the traditional audiovisual market, especially this last one, Netflix, that has become a broadcaster and a producer of content at the same time, entering different markets at the same time. These services have become an important threat for traditional broadcasters and telecom companies because they fight for the same audiences, offering the same or better content without a deployment of infrastructure and with new innovative business models. In the end, what is most important is the interactivity that these platforms offer. The consumer has switched to an active role in the digital era, and this is a key point. Both IPTV and over-the-top platforms represent a turning point in the sector. Television has stopped being a media exclusively owned by the broadcasters. New television providers have become direct competitors to traditional services, and now they almost lead the market. Let's finish now with the conclusions up to now. We go back to where we started. The broadcast sector has changed due to the big impact of the technological evolution. For most traditional telecommunication companies, radical changes to technology are not extraordinary. But what happened here is that the sector faces a big consumer behavior change and the emergence of new strong competitors. We have reconfiguring of the industry. Of course, we need to adapt to new changes. It is required to use the technology to arrive to a wider audience. We need to understand the consumer and give them what they expect. We also have new technologies that allow the convergence of networks and services. We have created the Anycast content. These 3 points together represent the transformation of the sector. The broadcast sector should rethink the business models and adopt a clear consumer approach. So At this point, you're probably thinking that you already knew what I tried to synthesize here, comes the big question: what do we do? And with this, finish. Nowadays, the consumer behavior within the audiovisual ecosystem can be taken apart from other related aspects of new times. A digital native's life, or maybe also a immediate user, it's surrounded by not only the new audiovisual consumption, but also by the independence that collaborative economy supplies. As a way to understand that this is a transformation of the sector and not just a group of changes, let me give you an example. Housing has suffered also a transformation. Who would think that people in 30s or mid-20s wouldn't be interested in buying a house? I won't. I pay rent and I share. Who would think that I wouldn't be interested in buying a car? I don't have one. I live here in Madrid and I don't need one car. If I want to move my car, I use Car2Go, eCultra, eMove. If I want to travel long distances, instead of searching for a bus or a train, what I use? I search for a BlaBlaCar, that they go to the same place that I want to go, and I choose the time, I choose the driver, and I choose everything. They have also a platform behind that rates the driver, so I decide to trust them or not. Technology has given me new possibilities and opened new markets by transforming the entire sector. We share cars, houses. We now share television platforms. New trends forward collaborative economy, but this economy focuses on the consumer. So even the consumer behavior seems to be unpredictable. It moves within these parameters. Total independence, best possible benefits, whenever I want it, wherever I want it. Who would finally end the fight between the operators and the broadcasters, or the over-the-top platforms? Network operators now find a really big paradox. Is digital a threat to, or an opportunity for our business models? If we invest in our infrastructures, maybe a different platform is going to use it and take advantage of it. There isn't a clear dominant in the broadcast television industry. All the stakeholders have now the same possibilities. It's up to them, it's up to us. Our industry will be unrecognizable in the 4 years. It is necessary to be prepared and alert to adapt to whatever comes. But this adaptation needs to be constant and quick. It has to be done fast. Investing in having a good and accurate information about both behavior of consumers and tech innovation all around the world is the only strategy. This is mandatory for technologists, for telcos, and for whoever wants to succeed or barely survives in the television sector. Thank you very much for listening to me.
Yes, Fernando, thank you very much for giving us an insight in the changes in the digital media and also the way of changes in the behavior of the users. And this is also very important today. I'm sure there will be questions, but please keep the questions to the end of the session. Now we go to the second presenter, and the second presenter is also coming from Spain. So Mrs. Noemi Merayo will give a presentation about, and it's a long title. It's Testbed technology for physical analysis in next generation Gigabit passive optical access network, GPON. I don't know if you know what GPON is, but very short, in the fiber to the building or fiber to the home, there are two main technologies. You have a fiber, a point-to-point fiber, where between the central office and the homes or buildings, there is one fiber for every user. Another technology is to use passive optical access, that's PON networks, where you have multiplex technology and you have less fibers. And it will go about the PON technology. So, our second speaker, Noemi, some information about her personally. She received a telecommunication engineer degree from the Valladolid University in 2004, and afterwards also a PhD in optical communication, also at the same university. She has worked as a junior lecturer at this university and also a visiting research fellow at University of Hertfordshire in London, working in the optical networks group. And her main research is focused on the design and performance evaluation of optical networks. Okay, Noemi, the floor is yours.
Thank you for coming to this talk. Thank you, Mr. Chairman, for your introduction. I belong to the Optical Communications Group at the University of Valladolid, which is led by Professor Evaristo Abril. And in this talk, I will explain how we use a real gigabit passive optical access network for research and also for learning tasks in our faculty. So the main motivation of this work is that we think very appealing that future telecom engineers can train some skills for their future careers, and regarding, for example, next generation networks based on fiber technologies. So in this way, in the access segment, passive optical networks are nowadays the more deployed architecture in the access segment. In Europe, the most important standard is Gigabit, based on, deployment is focused on Gigabit GPONs. So this kind of access networks can be analyzed from 2 points of view. The first one is how to provide quality of service inside the network, and for example, to create services, user profiles, and to control some quality of service requirements, such as, for example, delay, bandwidth demand, packet loss rate, jitter, and so on. And on the other hand, it is very important to take into account the analysis of the physical layer in the channel transmissions of this kind of networks. So in this talk, I will focus on this kind of analysis. First of all, I will explain how it's a gigabit PON architecture. It's very easy. And as we can see here, there is an OLT, optical line terminal, that's located in the central office, and by operators or service providers. And in the other side of the network here is the ONUs, several ONUs, or ONTs, optical network units or terminals, that is located inside the homes or the houses of users. And the topology is very easy. It's a tree topology between the OLT and the final users. And as we can see here, this distribution is done by means of a very easy passive optical splitter. The end-to-end distance is the standard set around 20 kilometers or up to 25 kilometers. And the idea is that this access kind of access networks works in 2 independent channels. The first one is the downstream from the OLT to the users, and the upstream, that is a point-to-point connectivity between the users and the OLT. Both of them works in a different wavelength, as we can see here. If we see here in the upstream direction, if all the users transmit at the same time, perhaps there can be a collision of data, of information in the optical splitters. So it is very important to integrate any kind of medium access control protocol. The standards, the POMs and standards use the TDMA, time division multiply access. It means that user transmit during a slot of time and information doesn't collide. So once I have explained how this kind of networks works, and I will explain how we deployed a 25 kilometers network in our laboratory. First of all, we use the devices belongs to the Spanish enterprise Telnet intelligent networks, and here we have the OLT. And as we can see here, there are 4 ports that support each of them up to 1 gigabit per second. The output of the OLT goes to this standard single-mode fiber. This single-mode fiber is up to 20 kilometers. And the outside of this fiber goes to the splitters. The splitters has 1 input and 8 outputs. As in a normal operation we only use 1 splitter, we can, for example, connect the 2 of them in order to achieve, for example, a 2-stage configuration. The output of the splitters goes to this fiber connection panel that connects this distribution fiber up to 5 kilometers. So depending on how we connect here, and the splitter, and here the ONTs of the user, we can reach a different distance. So we emulate a real situation in a real context. The user, the final user, is located from a different distance from the central office. And final, this panel is connected to the ONTs. These ONTs are the next generation ONTs, the 3-level ONTs, which means that the router and the optical device is integrated in the same device. The total end-to-end fiber length is 25 kilometers. So how we use the GPON testbed for teaching purposes? Okay, we start with a subject of the Ftth course, and to allow physical analysis of optical components and systems. So students in this kind of subjects have to learn how is the fiber propagation. They have to learn some characteristic of optical and components and devices. They have to know some optical propagation problems such as dispersion, attenuation, nonlinear effects, and so on. And they have to learn how to design optical network systems and to deal with instrumentation and simulators. So the lab sessions are divided in 2 different parts. In the first one, they have to use OpSync is a physical layer simulation platform. They have to mount very easy network systems, and they have to analyze, for example, the dispersion, the attenuation, and, for example, the bit error rate of the network. And on the other hand, they have to build real fiber connectors, and they have to do fusion splices with real optical networks. Moreover, they have to use optical time domain reflectometers, OTDRs, in optical links of, for example, 20 kilometers. So the idea is how we have integrate GPON testbed in our subjects. So in this basic subject, students have to analyze the GPON real network in the physical layer at both channels, at the downstream and in the upstream channel. And in a near future, this academic course, in the more advanced subjects, they have to know how to configure a GPON test, the GPON network, how to provide quality of service and to design services, and also user profiles. Very interesting for them. So here we can observe our testbed here, and the digital oscilloscopes they have to use at the OTDR, for example. So in the experiment, the first part of the experiment, students have to use the OTDR to analyze the 25 kilometers of the network at both the upstream and the upstream channel. So first of all, students have to familiarize with the OTDR. It's a very important device for an engineer. And they have to learn to configure the OTDR to detect the events in the 25 kilometers. Then they have to be able to interpret and to notice if these events are correct or not. For example, here we can observe 25 kilometers of fiber. As we can see here, the optical power is decreasing, because of the attenuation. The OTDR is able to detect the final end of the optical link, and here they have to know that there are connections here, these events, and they have to notice if these events are correct or not. In case they are incorrect, perhaps the network doesn't work. On the other hand, they have to use, in the second part of the experiments, some digital oscilloscopes, and at both channels, the output of the OLT, the downstream, in which they have to compare the optical and electrical IA diagrams, as you can see here, in green the electrical and in yellow the optical. Moreover, they have to learn how to measure the rise and the fall times of the laser or the OLT, of the OLT. And they have to measure the extinction ratio, the difference between the 0 and the 1, and also, for example, to measure the Q factor that corresponds to the bit error rate. Finally, they have to visualize the data frames, that is the information transmitted by the OLT to the different stations, ONTs. And they have to do the same, but in the other side, it means in the upstream channel. As we can see here, there are 4 stations that are transmitted in a very different slot of time, and each of them has a different optical power. If we do a zoom, we can observe the transmission of one of the stations. They have to learn what kind of information they transmit in the upstream direction. Finally, I will explain very short how we use the GPON network for research. So first of all, we have developed and programmed an intelligent network control module in Python in order to automatize the GPON configuration. It means the services and the user profiles in order to control the quality of service requirements in the access network. Moreover, we are trying now to integrate the famous OpenFlow standard in this kind of access networks, because this kind of access network do not support this kind of a standard. The idea is that any controller, for example, in that case, Open Daylight, can be able to control the configuration and the quality of service requirements of the access technology. And the idea to use OpenFlow is for a near future to introduce SDN, software-defined networks, and also the virtualization of networks. And in conclusion, we have deployed a real GPON network in our faculty for students, but also not only for teaching purposes, but also for research. And the testbed is used by the students of different subjects to analyze the physical layer of the transmission channels, and also to provide quality of service in more advanced subjects. Moreover, for us, it's very useful because we are applying some kind of research, trying to automatically configure the quality of service requirements inside the access network. And now we are working on how to integrate the OpenFlow protocol to control this access network technology. So that's all. If you have any questions?
Okay, thank you. I think this was very interesting, and I assume that the results are also interesting for the operators or for those who are rolling out now those networks, and it's a huge investment. We go now to the third speaker. Questions is for later. And the third speaker is Constantinos Papadias. Okay, it's obvious when you hear the name that he is coming from Greece. The title of his talk will be Single and Multiple RF Load Control Parasitic Antenna Areas Operating at CM Wave Frequencies. Design and applications for 5G wireless access backhaul. So a long title, and we are curious to have your presentation about the presenter. Constantinos is the Dean of the Athens Information Technology in Athens, and adjunct professor also of the Aalborg University in Denmark. I don't know if you also speak Danish, not so much. He is a graduate of the NTUA and the ENST, where he got also a PhD. He was researcher Institut Eurecom, Stanford University, and also Bell Labs, and adjunct professor of the Columbia University and Carnegie Mellon University. So there are a lot of universities he worked for and he visited. So, Constantinos, please, the floor is yours.
Thank you very much. Okay, so hello to everyone. Very happy to be here. Thank you, Mr. Chairman. Thanks to the organizer for having me. So I know the title is too long, which indicates that, you know, the more specialized research becomes, the more long the title is. And I also know that the time is limited, so I'll try to be quite fast. I just want to say these are research results produced by my team and myself over the last few years. We've been working on this topic of low complexity antenna arrays, which we feel are a topic that has not been very much researched, but holds a lot of potential for future generation networks. You heard earlier today that both new radio and backhaul are going to be bottlenecks for future systems, and we believe that this technology holds some answers. Okay, so this is an overview of my presentation. I'll share a few preliminaries, and then I'll get into the core of it, which is suggesting pre-coding techniques that combine low complexity antenna systems with baseband computation for better capacity, either on the radio access side or on the backhaul side, especially in cases where we have rich scattering propagation. I'll show you some of the systems set up and some representative equations of the solutions that we work on, and I'll show some results towards the end. Okay, so you have heard most of what is in this slide already today. You know that the volume of mobile traffic is exploding, and this puts a heavy burden on both sides, a heavy burden both on the access side and the backhaul. And you know, it was mentioned earlier today that microwave backhaul is reaching its capacity. There's another trend that is happening with small cells. You see that there's a needs for backhauling, sometimes wireless backhauling, that is not in line of sight conditions. It's for much lower height access points that often are surrounded by scatters. And there, point-to-point microwave, the way we know it, is not applicable because, first of all, it's quite massive, it has a high cost, and also it's not fit for non-line of sight conditions. So we believe that there is a space for improvements in the backhauling of small cells. So the trends, you can see them here, is using, you heard it also earlier today, higher frequencies going up to all the way up to 28 gigahertz. Using multiple antennas, you heard about massive MIMO in the presentation by Orange. This is something that is happening, but it's still very complex, so we are looking for alternatives where you can have massive MIMO that doesn't have massive complexity, if we can. And dense small cell networks, as I mentioned earlier, are another reality that is happening. Okay, so antenna arrays. Antenna arrays is a topic that you hear more and more since 3G and on in every generation of wireless networking. You hear antenna arrays. What is happening now? You start hearing it more, not only for access but also for backhaul, and they go back to the basics of Maxwell and the basics of antenna array theory. As we know it from the 60s and 70s, antenna arrays have a number of degrees of freedom, and these degrees of freedom, you can use them for different things. You can use them to increase the gain in a certain direction, or you can use it to do spatial multiplexing, or to do some diversity, such as in the work that my friend Luis Castillo mentioned earlier. So what this new paradigm that we are looking into is trying to do is pretty much having your pie and eating it too, which means you want to have many degrees of freedom, you want to have a lot of spatial, let's say, selectivity, but at the same time you don't want to have a linear increase in the corresponding cost. And we have been exploring a lot this idea of single RF or load control parasitic antenna arrays in an effort to try to offer better compromises in terms of complexity and performance. So what is the main idea? The main idea is what you see here, that in the conventional antenna array paradigm, you have as many RF chains as antennas. Okay, now this is okay when you have a small number of antennas, but has already been shown to be problematic when you have a cell phone, where you cannot have as many RF chains as 8 antennas, for example, to do uplink MIMO. And certainly it's not okay if you have those massive systems that have 1,000 antenna elements, because the cost is really, really high. Not only the cost, the size requirements, the cooling requirements, the whole power dissipation. So we'd like to move from this paradigm to the one down here, where we have a number of antenna elements that may be high, but fewer RF chains. And how do you do this? Well, we go back to old analog antenna systems. All of you are familiar with the Yagi-Uda antennas that are used for over-the-air TV over many decades. And there the idea is that you may have only a single active element, but many, many passive elements that are very closely spaced to the active one, and they induce currents through mutual coupling. So Maxwell comes into play there and allows you to do things. So we think that this technology can be used in order to offer better compromise between complexity and performance. So that's the main thing in my talk. Now, we are exploring this in the specific presentation in order to do what? To drive to push towards its limits the capacity that you have either on the access side or on the backhaul side by making use of those hybrid, let's say, antenna arrays. So again, there's many ways you can use them. One is to keep the same number of RF units as we're doing here, and add to each active antenna a number of passive ones that are very cheap and are controlled via very simple circuits. Or you could, in this way, you would have the enhanced performance. Or what you can do is keep the same performance that you would have here, for example, in RFID systems, etc., and try to reduce the cost and complexity by having more antennas for the same number of RF chains. Okay, so now this is getting a little more technical. When you start talking about parasitic antenna arrays, one of the big problems is we could not apply the usual baseband array processing model that is very well known in the array literature. So to overcome this, we came up in one of the EU projects called HARP with a new model where, in fact, you map no longer voltages to voltages, but voltages to currents. And once you realize that, you have a model that is very similar to what we had in usual array processing. And then all the techniques that you use in usual array processing can be mapped into this mixed digital analog domain. So we think that was an important contribution. And based on this contribution, we can do the things that, such as what we're doing in this paper here. So, by the way, the currents, they relate to the input voltage through this equation. That is nothing else but a generalization of the Ohm's law. The only difference is that you have this mutual coupling matrix that is not diagonal anymore, and you have to play with the loads in this matrix in order to produce the desired currents. Okay. So what we are, maybe I'll try to skip this slide in the interest of time, but maybe I can use, okay, this slide here can show better what we're trying to do. So assume that you have 2 base stations, okay, on the access side. So this could be remote radio heads. Remote radio heads is one of the newest trends in next generation networks, controlled by a central unit. And these cooperate with each other in order to maximize the capacity of this channel here. So this is a channel between 2 base stations on this side and 2 base stations on the other side if you have a backhaul, or 2 mobile terminals if you had an access. Now, what we try to do here is to say, instead of trying to jointly optimize the system with all the complexity it would have, is to pre-generate a number of beams. So we have a number of pre-selected beams that each of those access points can generate, and we can compute this offline and design the circuits that produce those beams offline, so they're available and we can just simply switch between them. And then on top of that, do some baseband processing that is very simple, because for a system like that, it will be a 2x2 pre-coding system, for example, in order to eliminate any remaining interference between the channels that are next to each other in the same frequency. So by doing this, obviously, you have better spectral efficiency, because instead of using orthogonal access, you use coexistence between interfering channels, and you try to get rid of the interference both in the spatial domain and the interference domain. So these are just some equations to show how we can compute the data rate, so the capacity of systems like that. And this is just a snapshot of the schemes that we use for the precoding. So we use either simple zero forcing precoding with power allocation on top, or regularized zero forcing beamforming for the case of low SNRs. And as I said, on top of that, we do some water filling to fix the power allocation. So these are some results that show that there is a big gain, a large gain to be had on the order of 10 dBs or so if you use this sophisticated pre-coding compared to simpler techniques, which is what you would have if you didn't have all this approach. You used either omni antennas or you didn't do any pre-coding. So there's a lot to be gained by that, and we feel that the fact that you can have this large gain with very low complexity antenna arrays is attractive for next generation, either backhaul or access. So this is the slide of my conclusions. The idea is that we can offer quite large gains compared to conventional systems with low complexity techniques, and we feel that this is an attractive approach for rich scattering environments. So thank you very much.
Yes, thank you very much for this interesting but a little bit difficult presentation. It's very technical. Questions a little bit later. We come now to the last presenter, and this is Raf Meersman from Ghent, Belgium. He will talk about how increased availability of GIS data and PC calculation power allows to save millions of euros in an FTTx network rollout. So from the air we come back to the ground, to the fixed network. Raf will give, in his presentation, illustrate increasing availability of land-based and infrastructure-specific geographic information, how important it is. Also, he will discuss how powerful algorithms can be to automatically calculate an optimized network architecture, and he will demonstrate also some real-life savings that has been accomplished in the planning of FTTx networks. Raf started his career at COMSOF as a consultant in 1999 after graduated at the University of Ghent as telecommunications engineer. In 2005, he became CTO of COMSOF. In this role, he was responsible for the research and development of FiberPlanet, COMSOF's optimization engine for fiber to the X network planning. And in 2012, Raf became shareholder and also CEO of this company. Raf, the floor is yours.
Thank you, José, for the introduction, and good day, everybody. So indeed, I will talk about the fiber networks, fiber to the X, specifically about planning. So I'm talking about the new networks where this session is about, but I'm also a little bit talking about the automation and the role of engineers in that. So I think that fits very well in this Congress. First of all, there's a lot of Spanish-speaking people, I think. So because nobody can remember my name who's Spanish-speaking, I took the liberty of translating my name. So you can call me Rafael Mazombres. That's a literal translation into Spanish of my name. As José told you, our company has developed a software called FiberPlanet, and this is a global market. We are a global market leader into this niche domain of software to enable this kind of networks being planned. So we have customers in more than 70 countries worldwide, including most countries in Europe and North America, but also across the globe. I will take you first very quickly through some principles and status of FTTH. I think most of you will be maybe aware of that, so I'll go quickly through that. Then I'll focus a bit on the challenges and opportunities of planning such networks, and then I will certainly spend most time on the enablers of this kind of opportunities. So starting with a brief view on FTTH. FTTH is in the market, in the telecom market for a long time, but it's now really at a point where it's breaking through. This is an official global ranking of countries with a percentage of FTTH deployment. This is the source is FTTH Council Europe. What's interesting to see is that there are some countries, especially in Asia, with a very high percentage already covered with fiber. So those are front runners. And Europe is coming behind that, but is taking some steps lately to close the gap, I would say. Also Spain, for example, in this list is on the list to the bottom, but this is more than a year ago. So in the meantime, Spain has even done a big work in this, and I'm sure Spain will be in the next thing much higher, because there's been a lot of fiber to the home deployment in Spain recently. And actually what I was mentioning of fiber to the home is no longer a debate whether it will happen. This figure nicely illustrates that that turning point is happening worldwide. Of course, also driven by these large deployments in Asia, and including even countries like China or India, where fiber networks are being deployed heavily. So fiber is becoming the most widespread access infrastructure worldwide. Now, there's also a lot of questions and discussions about 5G and whether 5G is a competitor of fiber to the home. But it's, I think, in the meantime, very clear, and that was also confirmed by previous speakers, that 5G and fiber is complementary. You need fiber for the backhaul of 5G, and this is also illustrated by this recent press release from a study by Deloitte, specifically here for the US. So that as a brief introduction to the domain of fiber to the home. Now I want to dig into a bit more detail about planning such fiber to the home networks. And when we talk about planning networks, we can identify different stages in a process, in the process of planning these networks. You can go from a business case planning, which is about deciding how much network will cost and where you might go with a fiber to the home network. You can talk about planning in a sense of comparing technical scenarios, like the GPON network. Okay, you can have splitters in such a network, but you can decide where you put those splitters, and that will influence the cost of your network, but also the performance. And ultimately, you want to build a network, so you'll have to plan a rollout, a construction plan that you can hand out to a construction company to build your network. Now, in each of these domains, we have experience and toolings to support those, but given the limited time, I will now just focus on the business case planning and look a little bit at the challenges and opportunities there. When we talk about the business case, we talk about maximizing profits, and to make it very simple, that's not a very mathematical equation, but still a very important one. We talk about revenues and costs, and the difference between that will be our profit. And in a fiber to the home network, there are a lot of parameters which will influence those revenues and those costs. Looking at the costs, for example, it is a very expensive network to deploy because there's a lot of labor involved, and labor is very expensive. So we're talking about order of maybe 400-500 euro per home, up to even in some countries and some areas 2,000 euro per home. So if you look at that on a national scale, that is really billions of euros which would go into this infrastructure. But if you're making a business case for such a deployment and you're looking at a certain city or a certain area, to determine that cost, let's take an example of a city with 50,000 homes, about 150,000 inhabitants. What would be the cost of such a fiber to the home network? It's of course crucial for your business case to know that, for the investors to know when they will earn back their investment. But to determine that cost, people used to use some Excel modeling, and they might look at the length of the streets in an area and then use that as a measurement to estimate costs. I call that guesstimating. So the ultimate thing to know really what a cost is with a certainty that is sufficient is to really calculate that network. And calculating that network, we are talking about an access network. So if you zoom into an area and you see there some streets with buildings and points representing the access for the fiber into the building, calculating a network design would actually mean to determine where the cables will be installed, where they cross the street, where you install a cabinet or a manhole along the street. So this is like a graphical view of such a network plan that is calculated for this area. From such a plan, you can exactly determine how many kilometers of trenching you need, how many kilometers of ducts, cables, how many splices, etc. So you can actually derive all the components, and for each component you know how much it costs, and that way you can actually construct a whole cost overview for such a deployment in a very accurate way. So that is the ultimate manner of preparing your business case, because this gives you a high certainty, and we've been involved in many such cases where our cost estimations would be like within a 5% margin of what would actually be the cost after installing the network. So based on such numbers, you can really build a safe business case and minimize the risks. And the reason to do it like this and not just to take some benchmark figures or some high-level figures is because, like I said, there's a lot of things influencing costs. For example, density of homes, whether there's a lot of apartments with multi-dwelling units, will have a big impact on the costs. And this is just illustrated here through 20 different areas, randomly selected and covering different types of areas, where you see the cost per home, like I said before, varying between anything like 400 and 2,400 euro per home. Of course, then you see it's very important to know in which type of area you are looking to deploy to know what will be the cost. And that's, for example, on a higher level, even national-wide, we've done some projects with operators to calculate the cost of a complete country, so to actually determine the network across all the cities and produce a kind of a heat map. This is ideal input to decide which cities or which areas you would deploy your network because of the cheap cost, the green ones, and which ones you would reconsider because they're too expensive at the moment. So preparing that business case, we want to make sure we get an accurate estimation of the cost, and then as such we can also make the right decisions for the business case, and that can really make a difference of several percentages, and real-life cases have shown differences of 5 to 20% in increased profits, either coming from a decrease in costs or an increase in revenues. And again, if you look at a real-life example, and you would have like a 50,000 homes area. Well, there was one example, for example, where the investment is about 30 million euro for this network. And if you then look at 5 or 20% difference in your business case that you can make by this kind of analysis, it means that you're talking about a value of 1.5 to 6 million euro of doing it right. That's a huge amount. But one of the challenges, of course, if you look at the traditional way of calculating or designing a network, is of course the time it needs to really produce a detailed design, a complete design for this area. And that is where our software and our expertise come in, because we automate this whole process, or as much as possible, based on available digital information. And as such, we can actually make this kind of decisions also in the short time frames that are available within a business case study. So let's focus now on the enablers for doing this kind of detailed studies in an accurate way. And the first important thing is obviously data. Geographical data. This is a nice picture, a satellite or an airplane picture, which is crucial information and which is really becoming available at a fast pace for worldwide. Now, satellite picture is nice to visualize, but real digital data is much more important even. Digital data, which is really in a database, like points stored with an XY coordinate where you can calculate the distance between 2 points, and as such know how long a cable or a trench would be. So this is an example of ideal GIS data that we could use and that where we could do our calculations on. So mathematical calculations on top of a, let's say, a graph. There's more and more sources available for this kind of GIS data, even open sources. If you're interested in this topic, just out of curiosity, have a look at OpenStreetMap. This is like a community-driven platform where everybody can actually document his own area, can add buildings, streets into a global platform, and where you find amazing amount of digital information, geographical information, and that is also just accessible for everybody. So there's a lot of applications that are starting to build on top of this open data. Of course, that's not perfect as it's driven by volunteers and the community. If you really want detailed and accurate information, we see also public authorities more and more investing in a very good digital cadastre, documenting how all the buildings and infrastructure in a city is installed. And also there's private data brokers more and more because there's a lot of value in this data. And their mobile mapping is also a very interesting new technology to capture that data. Just a few quick examples. I'm not an expert of the Spanish situation, but if you look at cadastre, and you see there's, for example, also in Spain, a whole web interface where you can actually get access to digital cadastre data. And this is available in almost all European countries nowadays. So you see, you can get access to all this kind of information about buildings, streets, etc. And the future is even probably a 3D version, which is even more interesting. If you add 5G modeling with fiber, it will also be very interesting to see heights of buildings and line of sight analysis. That brings me to the mobile mapping as well, because that's what will be, that's typically the technology that will be capable of generating those 3D databases. Mobile mapping is like when a truck from Google drives the street with laser measurement tools and cameras. Actually, the smart software then that will translate all those measurements and all those pictures into a real 3D environment. And okay, we all know Google Street View as an example of such technology, but you have also even more professional systems where you can automatically detect cables or poles or even every little detail, and you can do line of sight analysis because it's a full point cloud. And coming back to the other source, the OpenStreetMap, here you see actually an extract of data of OpenStreetMap for Madrid. Actually, a little bit in the middle is where we are now, near the blue point normally. This is where we are today. So you see the whole environment around us is actually very well documented in this. And actually what we did for this is we took this area with 50,000 homes from OpenStreetMap, and we actually created a design for this complete area. So this would actually be a valid fiber to the home design for this area, covering 50,000 households in the neighborhood. And we actually put the central office right here in this office, in this building. I don't know where, but that's just a choice, of course, that we could make. So zooming in, you see central office is here, and you would actually see now that the design documents where our cables would go into the street and how we would connect all the buildings. And from that, we can derive a total cost for this network. So I'm running a little bit out of time, so I won't do the polling because the idea was to check, but let's say it used to take probably more than 2 months to make this kind of a design for this area years ago. It's reduced to a couple of weeks in the meantime with some automations, but actually we did this design in less than 2 hours. And using just my laptop or our standard laptops, which shows that also the calculation power of the hardware is reaching levels where this kind of complex mathematical calculations can actually be done on a large scale using our latest software version. And you see, it took us about an hour to gather the public data available, and it took us about half an hour to let the software calculate and optimize the whole design for this area. So that's what I wanted to share with you. There's, from our perspective, a strong evolution in availability of sources and calculation power and intelligent algorithms, which are all evolving very quickly, and the combination of those aspects actually enable us to automate and optimize the whole planning, and as such save millions of euros in fiber deployments worldwide. Thank you very much.
So, thank you, Raf. We are running a little bit over time, 5 minutes. It was a real challenge to have 4 speakers in 1 hour. Not so obvious. Maybe we still have a few minutes, and we can have 1 question for each speaker in a few minutes. And if there will be more questions, then you can talk also to those speakers during the lunch break. So, are there some questions from the audience? It was all presenters were so clear that there are no questions we're raising. Really? Or you're very hungry, everyone? That's an alternative. Okay, maybe, okay, because of we are 10 minutes over time, okay, the best thing is that if you want to talk to those presenters, you can do this during the lunchtime. So I would like to thank all the speakers for their very interesting presentation. It was different angles about the new networks, so the digital networks. Fernando, Noemi, Constantinos, Raf, thank you very much for presenting.